Hey there. So last time we were talking and we defined what the inverse matrix was. We found a way to find inverses if the matrix was a 2 by 2, and we indicated that eventually we'll be able to figure out how to find matrices or inverses for matrices in general. So that's what we're going to work on today. And so we start with this definition right here. So matrices A and B are row equivalent if B can be obtained from A by a sequence of elementary row operations. Remember, I usually abbreviate that EROs. So if we start off with A and we have this other matrix B, if by performing some elementary row operations to A, maybe it takes 3 of them, maybe it takes 10 of them, who knows, it doesn't matter how many it takes. If by performing some collection, some sequence of elementary row operations to A, you eventually end up with the matrix B, then you say that the two matrices are row equivalent. So let me give you an example here. So here's the matrix A. Here's my example. And I'm going to just go 1, 2, 3, 4, 5, 6, 7, 8, 9. So here's my matrix A. And the matrix B, it's going to be 4, 5, 6, and then 5, 7, 9, and then 7, 8, 9. So I'm going to call this matrix B. And my claim is that these two matrices are row equivalent. So here's how to verify that. What I want to do, I'm going to start with A. The first thing I would like to do is interchange the first and second rows. So that would give me a 4, 5, 6, 1, 2, 3, 7, 8, 9. So there was an elementary row operation. One of them is interchanging two rows. Now, if I take row 1 from this matrix right here and add it to row 2, notice what I get. I get 5, 7, 9 in that second one. So by performing 1, 2 elementary row operations, the first interchange, the second add the first row to the second row, right? We end up with B. That tells us that these two matrices, A and B, are row equivalent. Okay, now for our next definition, a matrix, and I want to call it, well, I guess I'm not going to give it a name. So a matrix obtained from capital I by performing a single elementary row operation is called an elementary matrix. Right? So if you start with the identity matrix, n by n identity matrix I, perform a single elementary row operation to that. The resulting matrix is called an elementary matrix. So for example, how about 6, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1. There's an example of an elementary matrix. Why is that? Well, if you take the 3 by 3 identity matrix and multiply the first row by 6, right, the result is this one. Another example. How about 0, 1, 0, 1, 0, 0, 0, 0, 0. Oh, sorry, 0, 0, 1. here's another example of an elementary matrix. How is that, or why is that? Starting with the 3 by 3 identity matrix, if you interchange rows 1 and 2 of the identity matrix, you get this one. So here's another elementary matrix. And let's do one more. So my next example, also a 3 by 3. Let's go 1, 0, 0, 0, 1, 0, and 0, 4, 1. So what did we do to get this one? Well, if you start with the 3 by 3 identity matrix and do 4 times the first row and 4 times the second row and add it to the third row, you get this one. So here's another example of an elementary matrix. Okay, so now we have the following theorem. It goes like this. So if B is the matrix obtained from A by applying a single elementary row operation, and E is the elementary matrix obtained from capital I by applying the same elementary row operation. Then B is equal to E times A. This is cool. So here's what it's saying, right? We start off with A, perform a single elementary row operation to A, and you get the matrix B, right? So maybe you interchange rows 3 and 4 of the matrix A. That's the matrix B. If you apply that same thing, so in this case what we would have is we interchange rows 3 and 4 of the identity matrix to get this elementary matrix E. Then this multiplication right here gives us the matrix B. So E times A equals B. So a way to think of this is elementary row operations can be obtained by doing left multiplication by an elementary matrix. All right, so let's try an example here to see how this works. So let's start with our matrix A. Let's do the same one we were doing before. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And let's see. Yeah, let's just interchange rows 1 and 2. So B has been obtained from A by applying a single elementary row operation. In this case, we're interchanging rows 1 and 2. Okay, now what I want E to be the 3 by 3 elementary matrix obtained from I by applying the same elementary row operation. So in this case, I want to take the identity matrix and interchange rows 1 and 2. 0, 1, 0, 1, 0, 0, 0, 0, 1. Okay, so this is the matrix that you get from the identity by interchanging rows 1 and 2. So check this out. If I do E times A, so let's see, that will be 0, 1, 0, 1, 0, 0, 0, 0, 1 times 1, 2, 3, 4, 5, 6, 7, 8, 9. So let's see what we get when we actually do the multiplication. Okay, so what do? I'm going to take the first row, dot it with each of the columns, And so what do we get? Well, I'm going to get 4, then I'm going to get 5, then I get 6. Now I take the second row, dot it with each of the columns. That will be a 1, 2, 3, and then we'll get 7, 8, 9. Right, so you can check this multiplication right here. So this is amazing. What this shows is that we can perform row operations by matrix multiplication. Elementary row operation can be obtained by multiplying by an elementary matrix. I'll just write this as an observation. If E is elementary, then E is invertible, and E inverse is also elementary. So E inverse is elementary. So you might want to think about why that's true. Start off with an elementary matrix. Now, what does it mean to be invertible? It means that there is an inverse. Well, this elementary matrix has been obtained by applying a certain elementary row operation to the identity matrix. So, from our previous theorem then, there should be a way to undo that process. The undoing process can be obtained, right, by this matrix right there. Now, I'm going to write down a theorem. It's got a name, so this is called the equivalence theorem. And we will see this theorem throughout the quarter. And what's going to happen, we will get more and more parts to this theorem. So right now we're going to have 4 parts. By the time we're done, I think there'll be 15 to 20 parts to this theorem. And so it goes like this. For an n by n matrix capital A, the following are equivalent. So part A goes like this. Capital A, the matrix A, is invertible. Part B, the matrix equation AX equals the 0 vector. So when I put this boldface right here, I'm not sure if I mentioned this already, boldface around the number 0 means the column vector consisting all of zeros. So AX equals 0 has only the trivial solution. When we say trivial solution, remember that means all entries of x are equal to 0. Part C, let's put that over there. So part C, the reduced row echelon form of capital A is the n by n identity matrix. And part D, A is equal to E1, E2, dot, 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 En. Now, n is a bad choice. How about E sub k, where each E sub I is elementary. Okay, so this theorem, it's got 4 parts. And when we say the following are equivalent, what we mean is that if one of them is true, then they're all true. If one of them is false, then they're all false. So when we say the following are equivalent, if we have an n by n matrix and we happen to know that it's invertible, that means that this equation will only have the trivial solution. It also means that the reduced row echelon form of A is the identity matrix, and it also means that A can be expressed as a product of elementary matrices. Now, you've noticed we've had a few theorems so far. I think I've proved one of them. I've also stated a couple of them. So in this class, this is not a proof-based class in the sense that you're not going to be required to be proving difficult theorems. And so sometimes I will prove parts of theorems. In fact, I'm going to prove a couple of parts of this theorem in just a minute. I will also, as an exercise, ask you to do a couple of them. These are sort of not trivial, but these are easy exercises. They're worth working through. And so let's see. Well, let me put a couple of the parts here. So proof. Now, when we say they're equivalent, to prove that this theorem is true, what I'm going to do is first show that if A is true, that forces us to conclude that B is true. All right, so this is going to be the part. And I'll label it like this. Think of this as if A is true, it implies that B is true. Okay, so if A is true, that would mean that we can assume that capital A is invertible. And now what I want to do is show that the only solution to this equation right here is the trivial solution. So now what I want to do is, starting with the equation AX equals 0, right? I need to show that X equals the 0 vector. All entries are equal to 0. Now, by multiplying both sides of this equation by A inverse, we know that the matrix is invertible, so we can do that. What I get is X equals A inverse times the 0 vector. If we do A inverse times a vector consisting of all zeros, the matrix multiplication is going to give us the 0 vector. So that tells us that X, the solution, the only solution to this equation right here, has to be the vector that consists entirely of zeros. I also want to prove one more part. I'm going to show that if D is true, then part A has to be true. So I'm going to show that if we have A expressed as a product of elementary matrices, then A has to be invertible. All right, so I need a little room here. So we're going to now prove that D implies A. So let's assume that A is equal to this product E1, E2, dot, 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 E sub K. All right, so we're assuming that A can be expressed as a product of elementary matrices. What I need to do, I want to show that capital A is an invertible matrix. To do that, I need to show that A has an inverse. Well, this is easy. We said just a minute ago, that was our observation, that each of these matrices right here, each elementary matrix, is an invertible matrix. So E1 inverse exists, E2 inverse exists, and so on. So I'll just say check. This is pretty easy to see. Check. A inverse is equal to E sub K inverse, E sub K minus 1 inverse, dot, 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 E sub 1 inverse. So what did I do? I wrote this backwards and inverted each of the matrices. It's easy to see that if you multiply this times this, you're going to get a bunch of cancellation. You're left with the identity, and so we have a matrix, A inverse, so that A times A inverse equals the identity. And I'll just say exercise, or exercises. B implies C, and C implies D. Okay, so we've talked about the inverse matrix. We know how to find the inverse matrix for a 2 by 2. Now it's time to do this in general. So what we need is a procedure. We're about to write down a procedure that allows us, starting with an n by n matrix, capital A, by doing certain steps, we'll be able to produce the inverse for the matrix in the case that it actually is an invertible matrix. So this will be finding A inverse. So we've got an n by n matrix, and the algorithm for doing this goes like this. I'm going to write down a matrix, augmented matrix if you like, putting capital A, the n by n matrix, on the left-hand side. I want to put the identity matrix, the n by n identity matrix, on the right-hand side, and put a slash in between as a dividing line. So then, now I've got an augmented matrix. Right? I've got A on the left-hand side, I on the right-hand side. What I want to do is I'm going to do row operations. That will turn the matrix capital A into the identity matrix. If you remember, one of the parts of our theorem that we had a minute ago, A is invertible if and only if it is row equivalent to the identity matrix. The reduced row echelon form of A is equal to the identity matrix. So we do row operations. On the left-hand side, if we can get it to the identity, on the right-hand side, we will be looking at A inverse. All right, so now let's try an example. Oh, and before I do the example, so this can be carried out if and only if A is an invertible matrix. If not, we will get stuck. You will not be able to get A turned into the identity matrix. So let's say it like this. This procedure, or this algorithm, can be carried out if and only if A is invertible. Okay, so now I want to see this algorithm in action. The matrix that I would like to find the inverse for is this one right here on the right-hand side. So I've got 1, 1, 1, 0, 2, 3, 5, 5, 1. Right? Think of that as the matrix capital A. And we would like to find A inverse. So the setup is put A on the left-hand side, put a slash, put the 3 by 3 identity matrix on the right-hand side, and now I'm going to do row operations. I would like to get the reduced row echelon form of A. If it's the identity, when we get to the reduced row echelon form, then on the right-hand side, we will be looking at the inverse matrix for A. All right, now I got to do row operations. I got to take this slowly. So let's see. I've got a leading one right here. I've got a 0 below it. I'd like to turn that 5 right there into a 0 now. So what does that mean? Add -5 times the top row to the third row. 1, 1, 1, 1, 0, 0, 0, 2, 3, 0, 1, 0. Okay, so -5, that'll give me 0, 0, -5 plus 1 gives me a -4 there, -5 there, 0, 1. All right, so I did -5 times the top row, added that to the bottom row, there's the result. Okay, so I've got a leading one here, 0's below it. Now I move on to this one right here. That's a 2. I want it to become a leading 1. So 1, 1, 1, 1, 0, 0. I'm going to multiply the middle row by 1/2 so that I create a leading 1 right there. 0, 1, 3/2, 0, 1/2, 0, 0, 0, minus 4, -5, 0, 1. Hopefully you can see this okay. Right? All I've done from here to here, I multiplied the middle row, row 2, by 1/2. Okay, so now I've got a leading one here, and there's a 0 below it, so I can move to this next one right here. I've got a -4 there. I want that to be a leading one. So I'm going to multiply row 3 by -1/4. And it's just as easy, right? Anytime when you're doing elementary row operations, it's easy to make arithmetic mistakes. Take it slow. Okay, so what did I do? I multiplied the bottom row of this matrix by -1/4, so I get a 1, 5/4, and a -1/4 in that last entry there. Okay, we're in row echelon form on the left-hand side here. Now I want to get in reduced row echelon form. That means that I need to get zeros above each leading one. So as a first step, let's get rid of that top one right there. Right, so I'm going to subtract row 3 from row 1. 1, 1, 0. 5/4 minus 1, that's a -1/4 there. 0, 1/4 there. 0, 1, 3/2. 0, 1/2, 0. And 0, 0, 1. 5/4, 0, -1/4. And let me just make sure, it's always nice to have students to watch my arithmetic, and I just don't have it right now. So let's see, what did I do? Yeah, it's nice. It's nice teaching in front of a class so that you have students who can say, oh, you made a, that should have been a minus sign right there. They can catch arithmetic mistakes like this. So let's just make sure I did that right. So I'm subtracting row 3 from row 1. That gives me a 0 here. 1 minus 5/4 gives me a -1/4. And 0 minus -1/4 gives me a +1/4 there. Right, so I should be good. Next step. Now I need to turn that 3/2 into a 0. So I'm going to multiply the bottom row by -3/2 and add it to the second row. 1, 1, 0, -1/4, 0, 1/4, 0, 1, 0. Okay, now what do? I'm multiplying this by -3/2. So this is a -15/8. I'm adding it to the second row, so this becomes a -15/8. That's still a 1/2. I multiplied this by -3/2, so that becomes a 3/8, and so we get a 3/8 right there. Okay, last step. Now, so I've got zeros above this leading one. Now I need a 0 above that leading one right there. So I need to subtract row 2 from row 1. So we'll get 1, 0, 0. Okay, so I'm subtracting row 2 from row 1, which means I need -15/8. I'm subtracting it so that I'm actually adding 15/8 to -1/4. That should give me a 13/8. Okay, subtracting row 2 from row 1, so that gives me a -1/2. 1/4 minus 3/8. 1/4, 2/8 minus 3/8, negative 1/8. And everything else stays the same. All right, so notice what we've got. We started off with our matrix A, we did elementary row operations, we eventually got the identity matrix on the left-hand side. What we're looking at on the right-hand side, that matrix right there is A inverse. Elementary row operations give you lots and lots of opportunities to make mistakes. Be careful. Now here's another thing. Even when you start off with a nice matrix like this one right here, I've got all integers for A. Very rarely does the inverse matrix come out nice and clean. Almost guaranteed you're going to have fractions. It's going to be kind of a mess. But there it is, an algorithm starting with an invertible matrix, producing the identity there. Oops, there goes my chalk. Producing the identity here and A inverse over there. All right, have fun with that.